We'll look at how to obtain an initial feasible tree solution when we cannot easily obtain one by inspection. We'll be constructing what is known as the auxiliary network, together with a strongly feasible tree that determines a feasible tree solution for the auxiliary network, so that we can apply the network simplex method starting from this tree solution. And we'll end up with something that either tells us the original network has no feasible tree solution, or give us a feasible tree solution to the original network. Let's look at the method through an example. Here we have a network. The arc costs are not shown. To form the auxiliary network, we do the following. We first pick a node as our root, and in this case we're going to pick V4. And for every other node, we look at its supply value. If it is non-positive, we see if there's an arc from the root to that node. If there is, we add it to the tree. If there isn't, we create an arc and add it to the tree. In this example, V1 and V3 both have supply values non-positive, and there's no arc from the root to either of these nodes. So we'll create two arcs and add them to the tree. And the flow value put on these arcs are given by the negative of the supply values at the nodes that they point to. So for the arc V4, V1, the flow value will be the negative of -1, which is 1. And for V4, V3, the flow value will be 0. If the node has positive supply value, we see if there's an arc from that node to the root. If there is, we add it to the tree. Otherwise, we create a new arc and add that to the tree. So for V2, the supply value is positive, and there's already an arc from V2 to V4. So we take it and add it to the tree. And the flow value is given by the supply value at the tail. So the flow value we put on this arc is 2. And for the remaining arcs, the flow value is 0. And we can see that we have a feasible tree solution determined by a strongly feasible tree with T as its arc set. The costs that we put on these arcs are as follows. The added arcs are called artificial arcs, and they get cost 1. The remainder of the arcs will get cost 0. And if we apply the network simplex method, starting with this feasible tree solution, at termination, we must have one of the following. The feasible solution has a positive flow on an artificial arc, or the flow value on every artificial arc is 0. If we end up with a feasible flow with positive flow value on the artificial arc, then the original network cannot have a feasible flow. The reason is that if you take a feasible flow from the original network and put zeros on the artificial arcs, you get a feasible flow for the auxiliary network with cost 0. So if we end up with a minimum cost feasible flow for the auxiliary network with positive flow value on an artificial arc, the cost must be positive because the arc costs on the artificial arcs are all 1. And clearly, if the minimum cost flow for the auxiliary network has 0 flow on the artificial arcs, we can simply remove these arcs and we'll end up with a feasible flow for the original network. We'll now run the network simplex method on this example. So here, we're starting with this tree. And the flow values are 1, 0, and 2 on the tree arcs, and 0 everywhere else. We now go to step 2. We're going to set y4 to 0. And for each tree arc, the y value at the tail minus the y value at the head must equal to the arc cost. If we look at the arc V2, V4, the arc cost is 0, so y2 must be 0 as well, because 0 minus 0 is 0. And we need y4 minus y1 to equal 1, so this must be -1. And for y3, we need y4 minus y3 to be 1, so y3 must be -1. Next, we need to find an arc such that the y at the tail minus the y at the head is greater than the arc cost. In this case, we have such an arc V2, V1, since y2 minus y1 is 1, and the arc cost on the arc V2, V1 is 0. So this will be the entering arc. So if we add it, we have a cycle, and the arc V4, V1 is the only reverse arc in this cycle. So this will be the leaving arc. And theta will be 1. So after updating the flow, we'll get 1 on the arc V2, V1, 0 on the arc V4, V1, and so that leaves the 3. And the flow value on the arc V2, V4 will decrease by theta, so it goes from 2 to 1. And now let's work out the y values again. So y3 is as before, -1, because we need y4 minus y3 to be equal to 1. And y2 is again 0. And y1 is also 0. And in step 3, there's no entering arc that we can choose. And so this is a minimum cost feasible flow. But as you can see, we still have an arc in the tree. There's an artificial arc. So if we remove the artificial arcs, we will have a feasible flow for the original network, but we won't have a tree with 3 arcs. But what we can do is, since every non-tree arc has flow value 0, we can keep adding arcs until we get a tree with the right number of arcs. So I could choose to add in V3, V1, V3, V2, or V3, V4. So let's add V3, V2. And the tree with this arc set will determine a feasible tree solution for the original network. But notice that the tree here is not strongly feasible. And in fact, if we insist of keeping V4 as the root, there's no feasible tree solution determined by a strongly feasible tree. And in a separate video, we saw how we can deal with this. In this case, the network is actually decomposable. To see that, notice that in the original network, there's no arc going into V3. This arc here is artificial. And the supply value at V3 is 0. So none of these arcs can have a positive flow value in a feasible flow. And so they are useless and we can remove them. So in essence, we are really just looking for a feasible flow in this network.